Hey, welcome back. We're going to be talking about our chapter on electrochemistry here in chapter 25 and 26. So understand that one of our first topics that we're going to be talking about are what are called voltaic or galvanic cells, which are, in other words, like batteries. You interact with voltaic or galvanic cells every day. Anytime you interact with anything that has a battery in it, this is what's happening. So batteries, of course, like inside your devices or maybe in your car or something, they're a lot more compact, they're a lot more high-tech, but this is what we're going to be talking about is just kind of the natural science that's happening in a battery. So if you want to take a second and pause, I got to scoop my noggin out of the way a little bit. If you want to take a second and pause and copy down this model of a voltaic cell, and then unpause, and we will talk about what's happening in the cell. So did you pause? All right, so let's talk about what's happening now. So we have two beakers here. In one beaker, we have a strip of copper metal, and inside that solution, or in that beaker, we have a solution of copper nitrate. And then in the other beaker, we have a silver metal strip, and in that beaker, we have a solution of silver nitrate. Now, both of them are connected to each other by something called a voltmeter. That's that kind of squiggly thing at the top. And the voltmeter measures charge, or it measures current, and sometimes it can also measure electricity. So it depends on what kind of meter we have. So like a voltmeter measures electricity, but an ammeter can measure current. And we'll talk a little bit more about that in a little bit. That thing in the middle, that kind of U-shaped tube that I drew somewhat not very U-shaped, is called a salt bridge. And the salt bridge is usually filled with some sort of salt, usually something like potassium nitrate. It's a really common salt to fill the salt bridge with. And we'll talk a little bit more later about what the salt bridge does. Now, let's focus in on the solutions for a second. It's important to know that in the beaker that's with the copper nitrate solution, the thing that's really important in solution is the fact that we have a bunch of copper ions kind of floating around in solution. And conversely, you would imagine that in the other beaker, we have a bunch of Ag ions just kind of hanging out in solution. This is going to be important later. Now, this is a battery, and if we were to set up this battery, it would conduct electricity. So what's happening and why is it conducting electricity? That's what we're going to cover as we continue to go forward. We're going to bounce back and forth between this diagram and the notes, so make sure that you're comfortable with doing that. Let's go ahead and dive right in. So, what's happening? Electrical current is flowing from the copper metal to the silver metal. Now, electrical current can also be defined as electricity. And electricity is actually, as you might remember previously in the class, electricity is just electron flow. So we're talking about a transfer of electrons from the copper to the silver, which must be a chemical reaction. Let's try and label that actually. Let's take a second and let's label the direction of our electrons. So I'm going to put arrows like this, and I'm going to say my electrons are flowing from the copper to the silver, right? So that's the direction of the electron flow, from the copper to the silver. Okay, let's keep going. So let's say, well, how do we know this? How do we know that the electrons are flowing from the copper to the silver? Why couldn't it be the other way? Well, this is what we observe. We observe in this procedure that we notice that the mass of the copper metal is decreasing by about 2 grams. And we also notice that the mass of the silver metal increases about 6.8 grams. So we have to assume that something is leaving the copper and going to the silver. And based on what we know about electrochemistry, which you will learn as we keep going, it must be electrons. So understand that we're kind of front-loading with a lot of information, and we're going to explain the little details as we go along. But these are just observations, almost like an example. So what's happening here is we also notice that the copper solution is becoming a darker blue. So we're talking about this solution here. It's starting to change color, and it's becoming somewhat of a darker blue. So why are all these things occurring? Well, these things are occurring based on the electrical flow, like the electron transferring from the copper to the silver. And how do we determine what the decrease in the copper metal and the increase of the silver has anything to do with any of this reaction? Well, we have to take a second and we have to take the mass of each, the grams that we started with, and convert them into moles. So let's take a second and let's do that. I said the grams we started with, but that was incorrect. What I meant was the grams that happened after all the transferring, right? So we know that we have 2 grams of copper, and we know that we have 6.8 grams of silver. See if you can do this for yourself. Silver is Ag, excuse me. See if you can do this for yourself. Take a second and convert both of these into moles, and then we can look at the moles. So pause and come on back when you're finished. So notice that when we convert things into moles, it actually becomes a little bit more interesting, doesn't it? We notice that we seem to be losing twice as many moles, or excuse me, we seem to be gaining twice as many moles of silver as we are losing of copper. Do you see what I mean? For example, if I were to take 0.0315 and multiply it by 2, I would get 0.0630. So that means for every 1 mole of copper that I'm losing, I seem to be gaining 2 moles of silver. So let's explore that a little further. What's happening is what are called half reactions. In each one of these beakers, half reactions are occurring. The half reaction that is occurring in the copper beaker is one in which copper is losing electrons, and the reaction that's happening in the silver beaker is one which silver is gaining electrons. So let's see if we can show that. We have 2 different choices here, right? We can show Ag gaining an electron, but that would make it like Ag minus 1. And that doesn't really make sense. So let's take the Ag plus that's in solution. In the right beaker, we have Ag plus. We know that's in the beaker, so this is possible for us to do. And it is gaining an electron, and it is becoming Ag, which lines up with our knowledge, right? Our Ag is gaining mass. So where are we forming that Ag? We're forming it here in this equation. Now what about the copper? The copper is losing electrons, so that means we're going to start with copper metal, and we're going to lose electrons, and we are going to become, oh, excuse me, I wrote that the wrong way. Copper metal, and we are going to lose electrons until we ionize, and then we become like this. Sorry, I wrote my electrons in the wrong place, but we're here now. So each of these reactions are called half reactions because they can't occur on their own. So notice that silver is gaining electrons to become silver metal. So silver ion is gaining electrons to become silver metal. Copper metal is losing electrons to become copper ion. But do you realize that these things are happening at the same time? The electrons that copper is losing are the same electrons that silver is gaining. So that means that they have to be together. This type of reaction is called a redox equation. So redox is short for reduction oxidation equation. And we're going to talk about what those terms mean in a second. But we can combine these 2 half reactions to give us a complete redox equation. Let's stack them on top of each other first and see how they compare. We have Ag plus, so that's silver ion, and its 1 electron forms silver metal. And then we have copper, which is going to become copper plus 2 and 2 electrons. And I want to add these 2 things together. But before I do that, I want to make sure that my electrons cancel, because you might remember this from previous in the class, but we never really want to have electrons in our balanced chemical equation. So I'm going to manipulate these equations to make sure that the electrons cancel. And the best way to do that would be to multiply the top by 2. So if I multiply the top by 2, my electrons now cancel, and then I just add everything together. So I have 2 Ag plus Cu gives me 2 Ag plus Cu plus 2. So again, this still aligns with the results that we saw in our observations. Our silver metal is increasing, because of course it is, it's a product, and our copper metal is decreasing, which makes a lot of sense. It's a reactant. So the reactant is being used up, the products are being formed. And again, the electrons lost from copper are the electrons gained from silver. These processes of gaining electrons and losing electrons are what are referred to as oxidation and reduction. Those are the kind of the vocab terms that we use when we're talking about electrochemistry. But let's, one other little observation. You might have thought to yourself, well, hold on, why is the solution turning more dark blue? Well, this is why. This is why the solution is turning more dark blue. Because as we are going through redox, we are creating more copper plus 2 ions, which are dark blue in solution. So the more ions we make, the more darker blue we're making the solution. So everything lines up with what we were expecting to see in our observations. Let's talk about a couple important terms, or at the very least, let's write down a couple things that we've actually already done. Understand that equations for two half reactions can be written separately, but each half reaction cannot occur alone. Again, the electrons lost by one thing are the electrons gained by another, so they both have to stay together. Electrons are shown in each half reaction, but due to electron flow, that's why chemical changes are occurring. So sometimes things go from ions to metals and metals to ions, aqueous things, to solid things. The electron flow is changing these things. It's happening in a chemical reaction. Two half reactions can be added to give an overall equation, just like we saw before. However, and this is a big however here, look at the nice big words that we're using, so this must be important, right? The number of electrons lost by one half reaction must equal the number of electrons gained by the other half reaction. In other words, when we add two half reactions together, the electrons have to cancel. We can't have electrons left over. So positive and negative ions migrate through what are called a salt bridge. So if you were wondering, like, what is that salt bridge at the beginning? The salt bridge exists to have positive and negative ions migrate through it, so it can stop what's called polarization. If the two solutions become polarized, they gain an electrical charge of their own, and then the redox stops. So what the salt bridge does is it shoots either positive ions or negative ions into the two different beakers, depending on the beaker, and it polarizes the beaker. Okay, so that's what's really occurring here, and that's kind of the science behind it. So let's talk about the terms that are involved in this process. Now, there is a little bit of vocab here, so please make sure that you take some time to become comfortable with the terms that we have to use in redox, because they are really critical to understanding what's happening. So understand that we have an idea called reduction. Reduction is when electrons are gained. And you might think to yourself, well, that doesn't make sense. You just said reduction. Reduction, you would think, means electrons are lost. But you have to kind of think of it almost backwards. We have to think about, well, what's really happening here is what's called an oxidation number. The oxidation number is reducing, but we're going to talk about oxidation numbers later. So you can kind of think about the charge. The charge is reducing because it's gaining negative ones, right? Electrons are negative ones. And I think if you remember that electrons are like adding negative one, it makes it a little easier to remember. So reduction means I'm gaining negative ones, right? So my charge is decreasing. Above, or in the reaction we saw before, the place that we would consider reduction would be the silver metal. The silver solution gained electrons and became silver metal. So this is what's called reduction. Oxidation, however, is when we lose electrons. So we have reduction, gaining electrons, oxidation, losing electrons. And in this situation, that was when the copper metal lost its electrons and became copper ion. Now, there are a couple ways to remember this, a couple mnemonics that people like. One that we here use at Valencia is Leo the lion says grr. So Leo means losing electrons is oxidation, says grr. Grr is gaining electrons is reduction. Another one that I've heard is the word oil rig. So if you know what an oil rig is, it's like those things that are out on the ocean that pump oil out from the seafloor. Oil rig, oxidation is losing, reduction is gaining. You can do either one. I tend to kind of lean towards the oil rig thing, but that's just because I think I've heard that one more in my life. But the Leo the lion says grr one is pretty good too. So again, whichever one you want to use, just make sure that you keep straight which one is which, right? Reduction is gaining, oxidation is losing. Okay, so let's keep going. So we have, of course, what we call redox. Redox is a chemical change involving the transfer of electrons. The thing that we saw before, that was redox. So the silver and the copper exchange electrons. That's a redox equation. Now let's talk about the battery itself. We have some terms that we want to make sure that we understand. There are electrodes. The two copper, or the copper metal and the silver metal, are called electrodes. And specifically, the electrode where oxidation occurs, that's what's called the anode. So let's go back. Let's go back and look here. If we're looking at this solution, which is the one where oxidation occurred? Is it the silver metal or is it the copper metal? Well, based on what we saw before, oxidation was occurring at the copper anode, right? Or the copper electrode. So we could label this as the anode. And the anode is negatively charged. So, again, that's where oxidation is occurring in this particular cell, right? Let's go back a little and let's get the other one. And then just a little tip here. Anions move through the salt bridge towards this electrode. So if we go back, we're going to bounce back one more time. If we go back and look at the salt bridge, if there are ions in this salt bridge, so like if there's a negative ion, it's going to pass through the salt bridge into that solution, right? Because the solution itself is becoming less negative. And let's think about that. So if I have copper and it's becoming copper plus 2, it is gaining a positive charge, right? It's becoming more positive, or in other words, it's becoming less negative. So the salt bridge sends negative ions through the salt bridge in order to keep that solution as negative as it was before. So it kind of keeps it balanced. All right, now let's go back. All right, so now we also have the other electrode, which is called the cathode. And the electrode, the cathode is where reduction occurs. So, and you could probably assume that through the salt bridge, cations flow through that. So let's go back and let's label the cathode. So you would probably assume that if the copper is the anode, then the silver is most likely the cathode. And the charge on the cathode is positive. The way that that makes it easy to remember is that cathode kind of sounds like cation, and cations are positive. Or there's a T in cathode, and T's kind of look like pluses, so the cathode is positive in a voltaic cell. So just keep that in mind. Now again, through the salt bridge, we are going to take positive ions, and those positive ions are going to flow through the salt bridge. Why? Well, if we look at the reaction that's happening here, we have Ag plus, which is becoming Ag. So we are decreasing the amount of Ag plus in solution, and that decrease in Ag plus means that our solution is becoming less positive, or in other words, it's becoming more negative. So in order to balance that, the salt bridge sends over cations in order to keep the solution positive, right? Because if it became too negative, then it would polarize and then it wouldn't work. So it's important to understand that in this particular cell, the electrons are flowing from anode to cathode. I like to say they flow from A to C. I feel like it makes it easier if you think about your alphabet, right? From A to C. And there's a couple of other ways that we can remember where things are as well. So if you look at even just the names of the substances, right? So the anode starts with an A, which is a vowel, and oxidation starts with an O, which is a vowel. So if you remember that the two that start with vowels are together, right? Anode and oxidation. And then a cathode starts with a C, which is not a vowel, it's a consonant. And then reduction starts with an R, which is also a consonant. So the two vowels are together, the two consonants are together, and that kind of makes it easier to remember. Anode is where oxidation occurs, cathode is where reduction occurs. Now, just keep that in mind. So, I'm sorry. In the examples above, I forgot to fill out that particular thing. The anode is the copper metal. We labeled that. And the cathode is the silver metal. Excuse me. Did that a little out of order. So a couple more terms for us to remember, and then we're going to be done. Let's talk a little bit about what are called the agents, right? So we have something called the oxidizing agent. The oxidizing agent is the substance that is responsible for oxidation, but it itself is reduced. Now this can sometimes get a little bit mixed up. So it's the thing that causes oxidation, but it itself is reduced. In the situation above, that would be the silver ions. Let's look. So if the silver ions are the thing being reduced, let's kind of label that. They're being reduced. How are they being reduced? Reduced means that they are gaining electrons, but where are they gaining electrons from? They are gaining electrons from the copper. So it depends on what you're looking at. You could say that the silver is taking electrons from copper. It is the oxidizing agent. It is forcing copper to oxidize by taking its electrons. It itself is being reduced, right? That's the idea. We also have something called the reduction agent, which you could probably assume. The reducing agent is the cause for reduction, but it itself is being oxidized. So in the sample above, we're talking about copper. So if we go back up and look again, copper is the thing being oxidized. Why is it oxidizing? It's oxidizing because it is giving its electrons to silver. So it kind of depends on the way you look at it. Either copper is being forced to lose electrons, or copper is forcing its electrons on silver. I don't know. It just depends on the way you want to look at it. But copper is giving its electrons to silver. It is forcing silver to reduce. Therefore, it is the reduction agent, but it itself is being oxidized. So you have to kind of keep that straight, right? So if anything is being reduced, it's also the oxidizing agent. If anything is oxidizing, it's also the reducing agent. We need to go over this a couple times. That's okay. This can get a little tricky. All right. So what else? Oh, so I'm going to do a little demo for you when we talk about this, or at least I'm going to try to have the time to do so. But when we do this demo, I'm not going to do this or this. So we'll fill in this box in class. Otherwise, I think we're done. So that's it. That is galvanic cells, also known as voltaic cells. That's it. We'll see you next time.